In this video, I'll be talking about damped oscillations. So understand, let's take a very simple example of simple pendulum. You know, in our real life, suppose that this is our simple pendulum, you will see oscillations like this. Suppose that you displace this simple pendulum a certain angle, let's say theta displacement, but while it returns, it passes through this point, but it does not go to theta angle. It certainly goes to certain angle alpha, which is of course less than theta, right? Or theta is greater than alpha. That means this time it is not reaching to original position. If it is reaching to original end, then this would have been the position P, but it is going up to P dash. So now further it goes like this, but it will not cover alpha angle. It will certainly cover certain angle beta, where beta is less than alpha, and then simultaneously this process like this is oscillations used to damp. Okay, so basically in damp oscillations, when during the oscillations energy is getting dissipated, though motion is periodic. Apparently is said to be damped oscillation. Okay, now question comes, why it happens? The reason is here. In real life we have this point of suspension, so obviously this point of suspension will be having certain amount of force, okay, because of the friction force and hinge, right? So it will be having certain amount of force which is applicable, and which is obviously external force, and of course there is air drag. So air drag and friction force at point of suspension, right? So that's why it is happening that energy is getting lost. So slowly you see in real life pendulum stops. Okay, so in ideal SHM we were not seeing that if we wanted to calculate the time period, but here it stops. Okay, now talking about damped SHM. Damped SHM. Okay, so in damped in normal SHM, we have seen F is equal to minus kx. That means force was proportional to displacement, but of course in the opposite direction. Here there is air drag also simultaneously. So if you have seen this definition, if you have understood it, then you need to understand that velocity will be opposite to the direction of the velocity will be opposite to the air drag. Obviously suppose that if this pendulum is moving in this direction, obviously air drag will be in this direction. So this air drag can be written as Fd, which is given by experimentally proportional to velocity's opposite direction. So air drag is proportional to velocity of pendulum, or specifically oscillations. That means Fd is equal to minus Bv, where B is the constant which is damping constant. and whatever I am writing, again I am writing for small oscillations. Okay, small oscillations. So here I can write net force during the motion F net will be is equal to Fd plus F, right? This was F net. So initially, because of Fx, this was minus Kx, and this is minus B into V, Fd. So now this time F net is equal to minus Bx plus Kx plus Bv. Clearly you can observe this time our equation is certain else. So this time we can write the acceleration A is equal to minus Kx plus Bv upon m, and then if you wanted to write, you can write A is equal to minus K by m x plus B by m into V, and now you can write A is equal to d2x by dt2 is equal to minus K by m into x, and this is B by m into dx by dt. Clearly you can see this differential equation, this form of differential equation is not in our syllabus, so we cannot solve this thing. So we will leave this thing aside. We will just remember the final result, which is important for us. Okay, so the important result will be here when we will be solving. So we'll be achieving that equation of SHM, damped SHM xt is equal to A into e to the power minus bt by 2m cos omega t plus phi or sin omega t plus phi, whatever you want to write, where phi is initial phase angle similar to the previous SHM equation. Initial phase angle, A is the maximum amplitude, B is of course damping constant, right? So everything is known for us, and simultaneously we used to get the value of omega, right, in our normal SHM. So this time the value of omega dash here I am taking, that would be under root of k by m. In previous equations when we solve, we used to get omega is equal to root k by m. This time k by m minus b square upon 4m square. Okay, so you need to remember this is going to be the value of omega, where omega is the angular frequency of damped SHM, right? So interestingly, the time period this time will be t dash will be 2 pi by omega dash, which is 2 pi upon under root of k by m minus b square upon 4 m square. So this is complicated this time, and now we can also draw the graph for the time period. So if we remove this thing, we can obtain the graph also, which is a decreasing graph for time period. So if you wanted to draw the graph like this, the equation of our damped SHM will be like this. Okay, so you can clearly see this is the value of A max amplitude. Okay, this is x with respect to t. Fine. So this is a decreasing function like this, obviously periodic, but having SHM for small oscillations, but decreasing one. Okay, and it is pretty clear from the graph that amplitude is decreasing one. So here this is the maximum amplitude, so amplitude, damped amplitude will be given as A into e to the power minus bt by 2m. So that likewise we can calculate the value of damped amplitude with this formula. Okay, yes.